We talked a little bit about two different data structures before. One data structure was the stack, and one data structure was the queue. Fun to spell because there are 4 vowels in a row. Now the stack acts like a stack of plates. When you put in a number, it goes to the top of the stack. You put in another number, it goes to the top of the stack. You put in another number, and it goes to the top of the stack. When you remove, you always remove the last thing that you put in. If you pushed a 6, pushed a 7, pushed an 8, and then popped, the 8 would come out. Now the queue, we usually think about a line in the bank, where a person goes into the queue, and then another person goes into the queue, and then another person goes into the queue, and they're coming in from one side, they get in line, and as the bank teller services them, they go out of the line in the order that they came out. And so that's what we're going to be talking about today. Now, we use a metaphor of the queue like people getting into line, but in this case, with computer programming, we might be using numbers, we might be using objects, we might be using characters, but the first thing that goes into a queue is the first thing that comes out. And so that's an ever-rotating type of a situation. So if we were going to implement a queue, it's easy to talk about the abstract data type, but if we wanted to implement it, there's 2 ways we can do it. There's always 2 different ways, and that is with either an array or with a linked list. Today we're going to be talking about a linked list. So if we wanted to do something like add a 6 to the queue, then add a 9 to the queue, then add a 12 to the queue, this is the order in which we do it. So we would think 6 is in the front of the line, and 9 is second in line, and 12 is third in line. When we do a remove, then we would remove the 6, then we would remove and get a 9, and if we hit remove a third time, we'd get the 12. And that's what we would expect if we were in line at the grocery store or in line at a bank. Now this kind of lends itself well to a queue, or to an array, because we think about it just like we drew the other metaphor, and adding things to the queue in this way. If we put a 6 into the queue, we'll just put a 6 into the queue. And then we're going to add a 9. We'd add a 9 into the queue. We add a 12, and we put a 12 into the queue. All right, into the array. And so now we have a 6, a 9, and a 12 in the array. And it makes sense when we're adding things. But in the simplest naive way, we say to ourselves, what happens when we remove? When we want to remove a 6, well, then it forms a blank space in the array. And so if we were to remove a 6, what would happen? All of the valid data would need to move down, and the 9 would now be in the front of the line, and the 12 would be in the front of the line. So removing with an array, implementing a queue, involves us, when we remove, we have to move everybody down. And if you think about it in the real world, that's exactly what happens at the grocery store. When the first person gets their checkout completed, then everyone in line, they say next, and everybody moves forward 1 step. And they move forward, the next person in line steps forward, then the person after that, then the person after that. We call that a cascade, where the 9 would move, and then the 12 would move. And we have to do that in that order so that we don't clobber each of the elements of the array. Now this is not the best way to do it, but it is the most straightforward and the way that most closely resembles the metaphor that we have of somebody standing in line at a grocery store. So the adding involves just a simple write to the array. For example, if we would add a 15, what would happen is, well, the 9, the 12, all of our existing data doesn't have to change. All we do is we would write the new element when we enqueue, or when we add, we write the new element into the open spot in the array. Now, one of the things that we want to keep track of is the size of the array. And by that, we don't mean the capacity of the array, we mean the number of valid elements. So in this case, we would say that size would equal 3. So the size of the number of elements is going to be 3. Here, the size is equal to 2, and here the size is, since we added, again equal to 3. Now if we think about the enumeration of the array, remember the arrays always start at 0, 0, 1, 2, and 3 in this case, and realize that if the size is 3, 3 also forms a convenient index indicating the spot in the array that the new element can go. So here the size is equal to 2, 0, 1, and 2. So the size always is the index of the open element, the open space where a new element would go were it to be added. So when the size is equal to 2 and we add 15, all we need to do is write the value 15 to the array spot 2 and then increment size. So when we do that, adding is relatively easy. Now realize that adding, it takes 2 steps. So it takes 2 steps. Number 1, writing to the array. The second thing we have to do is increment size. And since it's a constant number of steps, no matter how many elements are in the queue, we would say that this is a constant time operation, or big O of 1. So it's big O of 1, it's a constant time, in that adding to the array using this method has just a set number of steps. But now if we think to ourselves about the remove, if we have to remove, what do we need to do? Well, if there were a whole lot of elements in the queue, and we assume our data array is large enough, so if we have a whole bunch of elements that are in the queue, what happens? Well, if we say there are n elements in the queue at any given time, and when we remove, remember we're going to take this guy out, and that's what's going to be returned. But then remember that each of the n-1 elements has to be moved down. So we have to do a copy, 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 and cascade all of these elements down. So how many steps do we have? Well, we've got the 1 step for basically saving the value of the first element in the array to be returned later. And so we have the 1 step for reading that. Then we have n-1 steps, n-1 steps in order to do the cascade, and then we've got the return value. So we have to read it, then we have to cascade, then we have to return the value. Well, we don't really care about these overhead steps, but the key thing here is that we have n-1 steps in order to cascade everything down. So that means that remove is rather expensive when we compare it to add. When we remove, we have to do a number of steps that is proportional to the number of elements that are presently in the queue. So we would call this a big O of n operation. So using this method, adds are fast, but removes are slow. If you think about it, we could arrange this in the opposite way, such that we keep all of our elements in the, we keep the head of the line. Had we kept the head of the line always here and the back of the line in the 0th element, well, it would have just been flipped on its head. Then adds would involve cascading everything up, and removes would only take the last element. So if the line were reversed, then this big O of 1 and big O of n would be reversed. And so depending on the application, you might say, oh, okay, well, if I need adds to be really fast, and I don't really care about how long removes take, then I would want to use this orientation. However, if you were in a situation where adds could be slow, but removes need to be quick, then you could reverse the orientation of the line always keep the first element at the highest index of the array, and then you'd have, if you reversed it, then you'd have fast remove and slow add. Now, later on, we're going to talk about an algorithm that allows both of these to be constant steps, but that algorithm is a little bit more involved, and so we'll talk about it at a later time. So next, what we'll do is we'll go over the implementation of this in code form by typing along and compiling.